Okay, let's jump right into this explainer. Today, we're exploring one of the most extreme, mind bending, and honestly, just absolutely mysterious objects in the entire universe. We're going to break down exactly how black holes work, unpacking the dense physics, and those bizarre phenomena that make these cosmic giants so endlessly fascinating.
Now, right off the bat, we've got to address the ultimate cosmic puzzle. It's a paradox that has bugged scientists for years. Studying a black hole is basically like trying to solve a giant jigsaw puzzle made out of completely invisible pieces. Because by definition, their gravity is so intense that literally nothing, not even light, can escape them. So, if we can't physically see them, how in the world do we even begin to figure out what they are and how they operate?
Well, that brings us right to Section 1, the ultimate cosmic puzzle.
So let's start at the beginning. The violent birth of a stellar mass black hole kicks off when a massive star, we're talking at least 3 times the mass of our own sun, finally runs out of its nuclear fuel. Without all that outward explosive energy pushing against the star's own crushing gravity, the whole thing just collapses in on itself. This implosion triggers a phenomenal supernova explosion, blasting the star's outer layers deep into space. And what's left behind? A core so impossibly dense that it just keeps collapsing forever, giving birth to a brand new black hole.
But what's really wild is the sheer difference in scale when we talk about these things. On one hand, you've got those incredibly dense stellar mass black holes we just mentioned. They pack at least 3 times the mass of our sun into a sphere no wider than a typical city. But then, on the flip side, we have supermassive black holes. These are the absolute titans of the universe, packing millions, sometimes billions of solar masses. Almost every large galaxy has one of these behemoths anchoring its center. Our own Milky Way, for example, is constantly swirling around a supermassive black hole called Sagittarius A star. All right, moving on to Section 2, spotting the invisible.
Since we obviously can't see the hole itself, astronomers have to rely on some pretty clever observational tricks to spot its gravitational impact on the neighborhood. For instance, we track stars that are accelerating in these frantic, incredibly fast orbits around what looks like completely empty space. We can also pick up high-energy X-rays blasting from superheated cosmic gas, swirling violently around the black hole. And thanks to some amazing recent tech, we can now even record actual ripples in the fabric of space-time itself, gravitational waves that are sent out when 2 black holes crash into each other. And that brings us to a frankly staggering number, 3. During the historic LIGO discovery of colliding black holes, an astounding 3 times the mass of our sun was converted into pure gravitational wave energy. And get this, it happened in just a fraction of a second. To put that into perspective, our sun converts only a tiny, tiny fraction of its mass into light every second. The raw power generated by black holes is just completely off the charts. Which leads us to Section 3, Anatomy of the Abyss. So let's take a hypothetical journey, an outside-in descent, starting with the accretion disk. Think of this as the black hole's messy feeding ring. It's a blisteringly hot, incredibly bright, rapidly spinning disk of gas and dust. But notice that funny warped shape. Because the black hole's gravity severely warps the very fabric of spacetime, the light traveling from the back of the disk actually bends over and under the black hole on its way to our eyes. This process, called gravitational lensing, creates this crazy visual illusion of glowing humps on the top and bottom. You might also wonder why the accretion disk looks totally lopsided in brightness. Well, because the gas is spinning at speeds approaching the speed of light, we get this awesome effect from Einstein's theory of relativity called Doppler beaming. The gas spinning toward us gets visually amplified, appearing brighter and bluer. Meanwhile, the gas spinning away from us looks dimmer and redder. It's literally the exact same physics as an everyday siren changing pitch when an ambulance drives past you, just applied to light on a massive cosmic scale. Moving just a little bit closer in, we hit the photon sphere. This is a seriously trippy visual boundary where gravity is so strong that light from the disk actually orbits the black hole multiple times before it finally escapes out to us, creating these thin nested rings of light. At the same time, intense magnetic fields can grab hold of infalling matter and blast it outward as thin, focused jets of particles traveling near light speed. For supermassive black holes, these violent jets can stretch for hundreds of thousands of light years across the cosmos. It's just wild. And then we reach the point of no return, the event horizon. You can basically think of this as the black hole's definitive surface. Once you cross this boundary, the velocity you'd need to escape exceeds the speed of light. And since absolutely nothing can travel faster than light, anything that crosses the event horizon is officially doomed.
A really great way physicists describe this is by imagining a waterfall of space. Right at the event horizon, space itself is flowing inward faster than light can possibly swim out.
So the million-dollar question is, what lies at the very bottom of that waterfall? Well, general relativity predicts that all the matter falling in is ultimately crushed down into a single, infinitely small point called the singularity. Down there, matter reaches infinite density, and the curvature of space-time becomes infinite. It is quite literally the real-world equivalent of trying to divide by zero on a calculator. All of our current laws of physics just completely break down at this point, leaving us totally in the dark about what physically exists at the core.
Next up, Section 4, the noodle effect. Okay, let's lean into the morbid curiosity for a second. What would actually happen to a hypothetical astronaut who made this descent into the abyss? Turns out astrophysicists have a highly technical, completely terrifying term for your fate: spaghettification. Because gravity decreases with distance, if you fell in feet first, the gravitational pull on your feet would be significantly stronger than the pull on your head. These extreme tidal forces would stretch your body out vertically while simultaneously squishing your sides inward, literally compressing you into a long, thin string of human spaghetti. But here's the twist. Your specific demise actually depends entirely on the size of the black hole you fall into. Because stellar black holes are relatively tiny and compact, the curvature of space-time is incredibly harsh right outside the edge. You would be violently spaghettified well before you even reached the event horizon. However, a supermassive black hole is so gigantic that the tidal forces at its horizon are actually pretty weak. You could comfortably drift right across the event horizon alive, completely unaware of your impending doom, until you got much closer to the singularity, where you'd finally, well, meet your end.
Which brings us to our final stop, Section 5, the information paradox. Back in the 1970s, Stephen Hawking realized something that flipped physics on its head. Black holes aren't completely black. Because of quantum fluctuations in the vacuum of space, right at the edge of the event horizon, black holes actually emit a very faint radiation. This means they're slowly, constantly leaking energy. And as they radiate, they shrink. If left alone, over billions and billions of years, a black hole will eventually evaporate and vanish completely.
And right here is where we smash into a massive paradox. Quantum mechanics strictly mandates a core rule. Physical information, the unique data of the particles that make up a star, a planet, or a doomed astronaut, cannot ever be destroyed. But think about it. A black hole absorbs all that information and then slowly evaporates into nothing. The problem is Hawking radiation is completely thermal and random. It doesn't carry any of that absorbed information back out. So if the black hole is gone and the radiation is just random noise, where on Earth did all the information go?
Physicists have proposed a bunch of workarounds for this, including a cutting-edge, really fascinating theory known as the remnant solution. It suggests that at the very, very end of evaporation, extreme quantum torsion at the microscopic Planck scale creates a repulsive force that basically hits the brakes and halts the collapse. So instead of vanishing entirely, the black hole leaves behind a stable, perfectly microscopic remnant, weighing a practically unfathomable 9 × 10⁻41 kilograms. This tiny little speck would essentially act as a cosmic hard drive, locking all that original information safely inside forever.
The reason scientists are working so incredibly hard on theories like the remnant solution all comes back to that one fundamental rule. Information can never be lost. Because if information actually can be permanently destroyed by a black hole, it means our entire foundational understanding of quantum mechanics is totally flawed, and we'd have to rewrite the most basic laws of the universe from scratch.
Which leaves us with this final lingering thought. When a black hole eats a star and slowly fades away into the dark, does the physical history of that star simply vanish from reality? Does it get locked inside an invisible microscopic remnant drifting through the void? Or does it get transported somewhere else entirely, maybe even to another universe? We don't have the final answer yet, but every single new observation brings us just a little bit closer to understanding the greatest mystery in the cosmos.